Good morning, students. Our today's topic in the subject of physics is activity and half-life. In the topic of radioactivity, this is somewhat technical topic, so concentrate yourself. First, we are going to read the definition of the activity. The number of the decays of a radioactive source per second is called its rate of decays or activity. Now, the definition of half-life. The half-life of a sample of radioactive element is defined as the time taken for half of the unstable nuclei to decay. It is represented by T 1 by 2. So, this is the time in which half of the unstable nuclei is decayed. This is called half-life. And activity is the number of the decays of the radioactive source per second is activity. So, half-life. For example, the half-life of the radium is 1600 years. Starting with 20 grams of the radium, so this is the starting mass of the radium. 10 gram will have decayed after 1600 years because 1600 years is the half-life of the radium, in which half of the substance will be decayed. So if in the beginning there is 20 gram of the radium, after 1600 years 10 gram will have decayed, leaving 10 gram. And if then 10 gram is left, so that will take again 1600 years to decay 50% of the left mass. So the left mass was 10 grams. So in total there will be 15 gram left. 15 gram decayed after 3200 years, leaving 5 grams and so on. The number of the undecayed nuclei or activity can be found by the equations if the time elapsed is a multiple of the half-life. And the equation is n is equal to n naught into 1 by 2 raised to the power n. This is actually the number of the undecayed nuclei or activity can be found by the following equations if the time elapsed is multiple of the half-life, where n is the number of the undecayed nuclei, n naught is the initial of the undecayed nuclei, and n is the number of the half-lives. So, another form of the equation is A is equal to A naught into 1 by 2 raised to the power n, where A is the activity of the radioactive source, A naught is the initial activity of the source, and n is the number of the half-lives. The graph shows a decay curve for a radioactive substance. From the graph, it is noticed that the number of the undecayed nuclei is halved when a time interval of one half-life has elapsed. For example, in the graph, you can see this is the initial. So after a half-life, half of the substance is decayed. Then in further half-life, so T1 by 2 plus T1 by 2 will be 2T1 by 2. Further half of the substance will be decayed. Then plus another half-life will be added. So 2T1 by 2 plus T1 by 2 will be equal to 3T1 by 2. So another half-life will be, another half of the substance will be decayed. So this is first half-life, then further half-life, then further half-life. Look now, this was the initial substance. So divided by 2 will make this, further divided by 2 will make this, further divided by 2 will make this. This is the first half-life, T1 by 2. Add another T half 1 by 2 will make 2T half by 2. Add another T1 by 2 will make 3T 1 by 2. So this is the graph. Now we are going to solve a question. The initial count rate of the radioactive substance is 256 counts per second. and its half-life is 5 hours. So initial count rate was 256 and half-life is given 5 hours. What is its count rate after 20 hours? So 20 hours is the requirement. We will put 20 in the numerator and half-life is given, that is 5. So divide by 5 will give us 4. That is 4 half-lives. So actually we are required to find the count rate of this after 4 half-lives. So 4 half-lives stands for 1 by 2 into 1 by 2 into 1 by 2 into 1 by 2 multiplied by 256. So solve it on the calculator, will give you the answer. So this will be the count rate after 20 hours. And other question is here. The background count was found to be 20 per minutes. Given that the half-life of the radioactive substance is 6 days and the initial count rate is 540 per minutes, what will be the count rate after 18 days? So very carefully look at this question. Background count rate was given. So whenever background count rate is given and the initial count rate is given, so first the background count rate should be subtracted from the initial count rate. So 20 will be subtracted from 540. So initial count rate will be 540 minus 20 is equal to 520. So this will be the first step. Whenever you are given the background count rate and the initial count rate, so initial count rate will be found by subtracting the background count rate from this value. So this is actually the number which is initial count rate. So from here we will proceed now. Okay, what will be the count rate after 18 days? And 6 days is the half-life. So we will divide 18 by 6. 6 threes are 18. It means 3 half-lives are given in which we are required the answer. So it means count rate after 18 days will be equal to, so 3 half-lives are there, so 1 by 2 into 1 by 2 into 1 by 2 into the initial count rate. Solve it on the calculator, you will get 65 counts per minute. And after this you will add background count rate into this value again. Therefore the observed count rate after 18 days will be 65 plus 20 will be 85 per minute. So this is the way. And other question is here. The radioactive element has a half-life of 40 minutes. The initial count rate was 1000 per minute. How long will it take for the count rate to drop to 250 per minute? So this is the first part. Then second part, and then in third part plot a graph of the radioactive decay of this element. Okay, first we are required how long will it take for the count rate to drop to 250. So look now, initial count rate was given 1000. In one half-life that will be 500. In another half-life it will be 250. In another half-life it will be 125. So up to this one half-life, then 2 half-life, then 3 half-lives. So it means when 250 count rate is, it has take 2 half-lives. The time taken for the count rate of 250 is 2 half-lives. That is 2 into t 1 by 2. 2 is remain here. And half-life is given, that is 40 minutes. So we will place 40 in place of t1 by 2. Multiply this number, that will be 80 minutes. This is the answer of the A part. In second part, count rate is 125 per minute. So up to 125, you can see this is 1 half-life, this is 2, and this is 3 half-lives. So the time taken for the count rate of 125 is 3 half-lives. 3 will remain as it is, and half-life is given 40 minutes. So 40 will be placed in place of t1 by 2. Multiply these numbers. So this will be the answer. Okay, in C part, we are required to plot a graph of the radioactive decay of this element. So look now, initial count rate was 1000. So look now, initial count rate was 1000. So we'll make a graph like this. Time will be taken on the horizontal line, count rate will be taken on the vertical line. So we will make a suitable scale. So here is 200, 400, 600, 800, 1000. So first was 1000 to 500, that is half of the count rate, that is taken by 40 minutes, because 40 was the answer of the 500 sorry 250 count rate was. Okay, 500 count rate was 40 minutes, then this was 80, then this was 120. So we will plot this data on the graph paper. So 5 will take 40 minutes, then 250 will take 80 minutes, then 120 will take 120 minutes. So this is the graph. These points will be joined with the help of free hand curve. And other question is here, the half-life of a radioactive element is 4 days. How long does it take for the 20 gram for a sample of the radioactive element to decay to 5 grams? So look now, in the beginning we are having 20 grams, half will be decayed, that is 10 grams, then 5 grams, because we want to reach up to 5 grams. This will take one half-life, this is another half-life. So the half-life of the radioactive element is 4 days. How long is required? So this is 4 days, this is 4 days, so it means there are total 8 days. So look now, this means that the decay process will have to go on through 2 half-lives. So the required time is 2 into t 1 by 2, and t's value is 4 days. So 2 into 4 will be equal to 8 days. And other question is here, a radioactive substance has an initial count rate of 240 counts per second. The count rate becomes 30 counts per second after 60 minutes. What is the half-life of the radioactive substance? So this is the total time given, from which 240 count rates come to 30 count rates. So first look, 240 is the starting. In one half-life it will be reduced to 120. Then in another half-life it will be reduced to 60. Then in another half-life it will be reduced to 30. So look now, the count rate is 30. We are actually have reached at the 30. So this is one half-life, this is 2, and this is 3. So it means 3 half-life is required to come to 30 count rates from 240 count rates. So this is the total time given, that is 60. So 60 divided by 3, because 3 half-lives are required. So 20 times are 60. So 20 minutes is the one half-life. And other question is here, a radioactive source has a half-life of 30 minutes. What fraction is left after 2 hours? So look now, it means 30 minutes is the half-life and 2 hours is the total time. In 2 hours we are having 120 minutes. So 120 divided by 30 is actually 4 halves. Okay, so what fraction is left? So let's suppose 1 stands for 100%. So in the beginning we are 100%. So after one half-life, 1 by 2 will be left. In another half-life, 1 by 4 will be left. In another half-life, 1 by 8 will be left. And in another half-life, 1 by 16 will be left. So one half-life, 2, 3, and 4 half-lives. So 1 by 16 of the fraction will be left after 2 hours. And other question is here, the table below shows how the activity of a radioactive source varies with time as recorded using GM tube and rate meter. So this is the time given and this is the counts given. Requirement is determine the half-life of the radioactive source. Okay, so from 4000 count rates, half count rate is actually 2000. So it means 20 minutes is the half life. So actually determine the half life is required, because from 2000 again half lives half count rates will be 1000. So again look 40. So it means 20 minutes is the half life. So the activity of the radioactive source decreases from 4000 counts per minute to half of its initial activity 2000 count rates in 20 minutes. For a further 20 minutes, from time 20 minutes to time 40 minutes, the activity is again halved. Therefore, the half-life of the radioactive source is 20 minutes. And other question is here. In 15 days, the activity of the sample of the radioactive bismuth decreases to 1/8 of its original activity. Calculate its half-life. So in 15 days, it is reduced to 1/8. So look, this is the beginning. So half of the activity, then further half activity, then further half activity. Half activity can be obtained by dividing by 2. So dividing by 2 will make a naught by 2. Further divided by 2 will make a naught by 4. Further divided by 2 will make a naught by 8. So 1/8 of the activity is this. So from here to here, one half life, then second half life, then third half life. So it means 3 half-life is required to go to 1/8 of the original activity, and it is given that 1/8 is reached in 15 days. So it means 15 divided by 3, because 3 half-lives are required. So 15 by 3 will make 5 days. So this is 1 half-life. And other question is here. A radioactive substance has a half-life of 5 days. If the mass of the sample of the element is 32 grams, what mass of the element is left after 20 days? So first we will find the number of the half-lives. So 20 divided by 5 will make the number of the half-lives, that is 4 half-lives. So actually we are given 5 half-lives in which the mass is required. So 1 by 2, because 4 half-lives. So 1 by 2 into 1 by 2 into 1 by 2 into 1 by 2. And the initial was 32 grams. So solve it on the calculator, you will get that will be the mass left after 4 half-lives. And other question is here. A laboratory keeps 4 milligrams of the strontium 90 with a half-life of 28 years. How much strontium 90 is left after 84 years? Again, very simple. First, we will find the half-lives. So 84 divided by 28 will make 3 half-lives. So it means in 3 half-lives, we are required to find the mass of the strontium. So 1 by 2 into 1 by 2 into 1 by 2, because 3 half-lives are there and initial mass was 4 grams. So solve it on the calculator. That is the answer that will be left after 3 half-lives. And other question is here. The graph shows the count rate for a radioactive source over a few hours. What will be the count rate after 20 hours? So 20 hours is the requirement. So look now, from 2000 to 1000, the time required is 5 hours. So 5 hours, and the requirement was what will be the count rate after 20 hours. Okay. So 5 hours, 1000, in another 5 hours, that will be 500. In another 5 hours, that will be 250. And in another 5 hours, that will be 125. So after 20 hours, count rate will be 125. So these are actually option given. So C part will be the answer. Look now, from the graph, half-life is 5 hours. After 20 hours, 4 half-lives are actually there. The count rate will be n naught into 1 by 2 raised to power n. Initial count rate was 2000 into 1 by 2 raised to the power 4, because 4 half-lives are there. Solve it on the calculator, you will get the answer. And other question is here. Which graph shows how the count rate for a radioactive substance varies with time? So understand one thing, radioactive substance count rate is always a curve, not a straight line. So we will ignore these two parts. C and D will be neglected. This can be answer and this can be answer. Okay. The thing is now half-life should be uniform. So from 400 to 200, this is the time, and up to 100, this is the time. So this looks uniform, but this is not uniform because 200 to 100, this is the half-life. But in another half-life, that is 50, this is not uniform. So A can be the answer. So look now, the decay curve is an exponential graph. It is not straight line. The time intervals for the count rate to be reduced by the half are constant. Okay, exam tip for you people is the time interval for the count rate to be reduced by half is in fact the half-life of the radioactive substance. It is constant. So student, this was very important topic. That is actually the topic was activity and half-life. Technical topic. Read this lecture again and make your notes. Thank you so much.